Let us continue our lecture this afternoon, right? So in the previous class, we were trying to solve this equation. For x is from 0 to L.
It's a negative f of x.
It's a negative. U0 is 0 and UL is 0. All right. So in the previous class, we need to solve the eigenvalue problem. All right. So theta n second is lambda n theta n for x from 0 to L, and theta n at 0 is 0, and theta n at L is 0, right? So in this problem, I put the n, and you have lambda, but it's gonna be the same if I ask you to do this, the following problem. This is equivalent with lambda plus lambda is 0, x is from 0 to L. Phi of 0 is 0. Phi of L is 0, right? So let me plus minus theta, right? This is a plus minus lambda, all right? So in the exam, in the homework, if I ask you to solve this problem, lambda, this is the same with this one. Here I put the n because I know in advance that you have lambda 1, lambda 2, lambda 3, lambda n, right? And I put the lambda on the right hand side. But it is the same with putting the lambda on the left hand side because you can just change the minus, the lambda to minus lambda, right? Because this problem is nothing but lambda n second plus minus lambda n, phi n is 0, and phi n at 0 is phi n, and L is 0. Then is the index. You have phi 0, phi 2, phi n. So those are all of the solutions. So if I remove the n, it's going to become this problem. You see, if you solve this problem, it's going to be, it's going to give you exactly the same problem, the same solution, lambda 1, lambda 2, lambda 3, lambda n, and it's just the index. You see the point? Right? So basically, this is equivalent with this, right? And this minus, so I drop the lambda n, I have this. And phi 0 is phi l. This is 0, right? So basically, if I ask you to solve the eigenvalue problem, you know that there will be several solutions, phi 1, phi 2, phi 3, phi n, right? But if I don't like, I don't put the index. But if you solve this problem, it's going to give you also phi 1, phi 2, phi 3, phi n, right? And if I remove the lambda, the minus in front of the lambda, it means that the eigenvalues change the sign, right? It's clear? Questions? Yes?
So you could solve the eigenvalue problem if leaving the negative outside, you just get a different answer for your lambda.
So if without the lambda, you just change the n pi square or something to the minus n pi square. Right?
Okay.
Right? So it's the same. It's exactly the same. Right? So if I put theta to minus lambda, I want to get this. Theta of phi is 0. Phi of 0 is equal to phi l, and this is equal to 0. Right? This is the one that I asked you to solve in homework. This is exactly the same. I explain again. This is the eigenvalue problem that we are solving. I put the n because I know that they have several solutions, phi 1, phi 2, phi n, right? Okay, so sometimes in the homework or in the text, in the notes, we have this problem, but they're equivalent, right? Why? Because now I put the minus the lambda and phi n to the left hand side. I put it to the left hand side, I have a minus lambda and phi n, right? So the n is the index. It shows that, okay, for this problem, you have countable numbers of solutions, Phi1, Phi2, Phi n. If I don't like the n, I just remove it, right? I get this problem. And if I put theta to be minus lambda, I get this problem, which is exactly the problem here. It's clear? Questions? It's good? All right. So let us drop the n and solve that problem. All right. But it's going to be equivalent. So the two problems are equivalent. Right? So now let us drop the n and solve the problem without the n, right? So let's solve this problem without the n. So which is this problem, right? So we have phi lambda minus lambda phi is 0 for x from 0 to L, and phi 0 is phi L, and this is also 0. Right? Let us solve this problem, which is this guy here. After I drop the n. Again, the strategy will be the same, right? Because this is a second order differential equation. So what you do is you consider the characteristic equation. So this will be x squared minus lambda is 0. Now you consider case number 1. Lambda is positive. Again, if here you have a plus, then you just change the sign, right? So when lambda is greater than 0, we know that, okay, you have two solutions, right? Two roots. The first root is square root of lambda. The second root is minus the square root of lambda. And then the phi of x will have to be of the form C1 exponential square root of lambda t x, right? Lambda x plus C2 exponential of minus square root of lambda x. All right? So this is the methodology so this methodology is always the same. The only difference is the boundary condition, right? So you consider three cases. You know that in the first case, you have lambda is greater than 0. When lambda is greater than 0, you have two roots, square root of lambda and minus square root of lambda. Then the general solution is of this form. The only difference is only the boundary condition, right? Boundary condition. Right? For this kind of problem, the strategy will be the same. The only thing which distinguishes one case from the others is boundary condition. Right? So now I'm gonna use the boundary condition at 0. V0 is 0, means that C1 is 0 plus C2 is 0 is 0, which means that C1 plus C2 is 0. So C2 is minus C1. All right? Good. Yes?
For the characteristic equation, we also do let x equal like e to the r or t or whatever, like in ODEs.
This is no.
Yeah, no, I know, but like write out those stuff. Okay, never mind. It's okay.
Ask again. So what is that?
Like, I don't know, in ODEs, we would say let x equal e to the rt, and then take the second derivative of that, and then plug that back into the equation for x.
No. So in the ODEs class, right? So in the ODE class, this is what you do. this is what you do in the ODE class. You have lambda second is 0. All right? You suppose that phi x is e to the rx, right?
Yeah.
You take the second derivative, right? So this gives you r squared. The first derivative will be r times e to the rx. The second derivative will give you r squared e to the rx.
Yeah.
Right?
And then you plug that.
You plug it back,
Yeah.
you get what? You get phi second x minus lambda phi x is then r squared e rx minus lambda e to rx. All right?
Yeah, that's it.
Yes, and this is minus lambda e to the rx is 0, which means that e to the rx, r squared minus lambda is 0, which is the step that we wrote here. So what you say is the derivation of the characteristic equation.
Okay.
We don't do that, we just admit the characteristic equation. So this is how you obtain the characteristic equation, right? So this is from ODEs. So you have phi second minus lambda phi is 0. So I didn't explain how you obtain this characteristic equation because this is from ODEs, but this is a chance for me to recall this for you. So the idea of obtaining this characteristic equation is the following. You suppose that the solution is exponential of rx. R is some constant, right? So you take the first derivative, it gives you r is rx, right? You take the second derivative, it gives you r squared is rx, right? So now you plug everything back into this equation. So you know that phi second minus lambda phi x is 0. So phi second is r squared is to rx, lambda phi will be lambda is to rx, right? So you put e to the rx outside as a common factor, and which means that you have r squared minus lambda is 0. All right? So this is basically the characteristic equation. Characteristic equation. So how do you solve this? You consider 3 cases, right? So for a characteristic equation, if lambda is greater than 0, you have 2 roots, lambda 1 and square root of lambda, and the second one is minus square root of lambda, right? So now you take the 2 roots, you plug it back to this equation, right? You get two solutions. The first one is theta 1 of x is e to the square root of lambda t of x, and phi 2 of x is minus square root of lambda x. So the solution will be the combination of the two. So you have C1 is square root of lambda x plus C2 is square root of minus lambda x. This is what we wrote here. It's clear? So basically what you said is how you obtain that characteristic equation.
Yeah, that's what I was, okay.
But after you have the characteristic equation, you solve it. You get 2 solutions, square root of lambda and minus square root of lambda. But in the beginning, you suppose that the solution is of the form exponential x. This is why you have 2 solutions, exponential of square root of lambda x and minus exponential minus square root of lambda x. And this explains why here you have the linear combination of the 2. All right? Questions? It's clear? Now, after I solved the characteristic equation, I found 2 solutions. The only difference in all of those problems is boundary condition, right? So the boundary condition change is gives you different values for lambda. It's clear? Now, phi 0 is 0. Then you get C1 e to 0 plus C2 e to the 0, which means that C1 plus C2 is 0, C2 is minus C1. I'm going to check the second condition. The second condition is phi L is 0, which is this guy. So from here, I know that phi x will be C1 e to the square root of lambda x minus C1 e to minus square root of lambda x. All right? So the second boundary conditions tell me that when I replace L here, I have a 0. So I'm going to have C1 e to the square root of lambda L minus C1 e to square root of lambda L. And this gives me C1 e to square root of lambda L minus e to minus square root lambda L. And we discussed that this is positive. Why? We know that this guy is positive from the previous class. Why? Yes?
Because e square root of lambda is greater than 1,
Yes.
and the other one is less than 1.
Can you stand at the back of the paper, please? Right? So from the previous class, we know that this guy is positive because e to the square root of lambda L is bigger than 1, and this is bigger than 1 over square root of lambda L, which is e to the power minus square root of lambda L. Right? Alright? This is strictly positive, which means that C1 is 0 and C2 is 0. So the solution is 0. We don't have anything in this case. Alright? Questions? Right? So I explain again. In this example, what we did is we removed the n. I mean, we know that there will be a series of solutions for the eigenvalue problem. This is why in the previous lectures I put the n. But in general, you can remove the n because after you solve it, you will see that this is a series of solutions, right? Now, let us look into this problem. You have phi second minus lambda phi 0, and with the two boundary condition. The method to solve it is the characteristic equation method. How do you obtain a characteristic equation method? Characteristic equation. So this is one derivation, right? So you suppose that the solution is exponential of something. You take the second derivative, you plug it back. You see that you will see immediately the characteristic equation. You see that r squared minus lambda is 0. So when this is 0, you have two roots, right? The two roots you plug back to this form. You're gonna have one solution square root lambda x, and the second one is minus square root lambda x. You combine them. And you get this form, right? So this is the same for all problems. Now the only difference is the bound between problems is the boundary condition. You know that phi 0 is 0. You plug 0 into this form, you're gonna get C1 plus C2 is 0, which means that C2 is minus C1. And phi x will be C1 exponential of square root lambda x minus C1 exponential of minus square root lambda x. You replace the boundary condition at L, you're gonna get C1 exponential of square root lambda L minus exponential minus square root lambda L. This is strictly positive because the first guy is bigger than 1 and the second guy is smaller than 1. So C1 has to be 0. If C1 is 0, C2 is also 0. And phi is 0. So you don't have any eigenfunction in this case. Questions? Screen? Right? So in the case that I put a plus here, if I put a plus here, I have to change this into minus lambda. So lambda is negative. But this is the same. You change the sign. Right, so now we consider case number 2. Case number 2. Lambda is 0. So lambda is 0. You don't need to use the characteristic method, right? So you have phi second is 0 phi, and this is 0. So what is the solution for this guy? Yes?
Ax plus b.
Yes. Can you sign the back of the paper, please? So for this guy, because phi second is 0, phi prime of x will be a constant a, right? You just take the antiderivative of 0, you get a constant. Now, you take the antiderivative of a constant, you're gonna get ax plus b. All right? It's clear? Questions? Right? So in the case lambda is 0, you have the equation phi second is 0 lambda x, 0 phi. So phi second is 0 means that phi prime is a. Then you take the antiderivative of a, you have ax plus b, right? So in this equation, you have two unknowns, not just one unknown, right? So what are the two unknowns in this equation?
L.
L is given. L is the interval. This equation has two unknowns, not just one. Maybe this. Yes.
The lambda and V.
Yes. Can you say the back paper, please? In this equation, we want to find the eigenvalue and the eigenfunctions, right? So in this equation, you have two unknowns, lambda and phi. This is different from the original equation. You have one unknown, right? So, for instance, this equation has only one unknown. You have to find u, right? You have to find u. But in this equation, you have two unknowns, the lambda and the phi. You have to find at the same time the lambda and the phi. This is why you have to consider three cases for lambda. Right? Lambda is not given. Lambda, you don't know what is lambda, right? This is why you have to consider all of the possible cases of lambda, right? In this case, you have two unknowns. Two unknowns. Lambda, this is the eigenvalue. And phi, this is the eigenfunction. Right? So this explains why you have to consider three cases for lambda. Alright? It's clear? Now, the case number 2. Lambda is 0. How can lambda is 0? When lambda is 0, you have ax plus b. For this solution, what should I do? Yes? Yes, can you sign the back of the paper, please? So you're going to use the boundary condition. All right? Again, this step and this step, they are the same for all eigenvalues problems. The only difference is the boundary condition. So the first boundary condition is phi 0. It's going to be 0. So 0 will be a times 0 plus b, which means that b is 0. So phi will be 8x, right? You use the first boundary condition. You see that phi of 0 is 0, then 0 is a times 0 plus b, right? So which means that phi is 0, so phi is ax. You use the second boundary condition. Then you're going to have what? You have a times L is 0, so a is also 0, right? So which means that phi will be 0. And this is not an eigen function. Questions? Right? So in this case, we have to consider all of the cases for lambda because we don't know the values of lambda. We solve an equation for both unknowns, the eigenvalue and the eigenfunction. You're going to find a function such that the second derivative is a multiple of the function itself. But we don't know the multiple, the factor lambda. It's clear? Questions? Now, for the third case, case number 3. Alright, so in this case, lambda is negative. So what happens when lambda is negative? Yes?
We get C1 cosine lambda or square root lambda x plus C2 sine square root lambda x.
Right. Can you sign the back of the paper, please? So when lambda is negative, x1 will be I square root lambda, and x2 will be minus I square root lambda, right? Then you have phi x will be C1, absolute value of lambda. Sorry. Cosinus of square root absolute lambda x plus C2 sinus of square root lambda x. All right. Questions? All right. So the third case is the case when you have an imaginary root. So because lambda is negative, you have x squared is going to be lambda, right? So x squared is lambda means that you have two imaginary solutions. The first one is I times the square root of the absolute value of lambda, and the second one is minus I times the square root, right? So then the phi will be C1 cosine square root lambda, C2 sine square root lambda, right? Questions? Yes?
Shouldn't that be when x squared equals negative lambda?
X squared is in, here I put minus lambda,
Oh, okay.
right? Yes. So I have a questions. So who wants me to review the derivation of the characteristic equation for second order differential equation with constant coefficient? Who wants me to review on that? Okay, so I'm gonna review. After this, I'm gonna review about that. Okay. Okay, so you're gonna have phi x is C1 cosine square root lambda and C2 sine square root lambda. All right. So what is the next step? Yes.
Plug in the boundary condition.
Yes. Can you stand at the back of the paper, please? Phi 0 is then cosinus of square root of lambda times 0 plus C2 sinus of square root of lambda times 0. And you know that phi 0 is 0. All right. So after solving this problem, I'm gonna go back and derive the characteristic equation and how you can solve a second order differential equation with constant coefficient. Right. Good. So you have 0 is phi 0, and I plug 0 back into those function. Right. What can I say about the two coefficients C1 and C2? Yes?
And you can say that C1 is equal to 0.
Yes. Can you say at the back of the paper, please? So this guy is 1, and this guy is 0. Right? So then you have C1 here, right? Because you replace 0 here, sinus of 0 is 0, cosinus of 0 is 1, so you have C1 is 0. Now the function is left with C2, sinus of square root of lambda x. All right? All right, so now what is next? Yes? Yes, can you say at the back of the paper, please? Now I'm going to use the second boundary condition, all right? The second boundary condition is phi L is 0. So when phi L is 0, you have C2 sinus of square root of lambda x L is 0, which means that sinus of square root of lambda L is 0. Questions? So sinus of what is 0?
Doesn't the square root of absolute value lambda L equal n pi?
Yes, can you stand back and paper, please? So you know that we know that sinus of n pi is 0. All right. So square root of lambda n L will be n pi, and square root of lambda will be n pi over L square. Lambda will be minus n pi over L square. All right. It's clear. So basically, because of this, you have multiple values for lambda. So lambda has multiple values. So we denote lambda by lambda n. And then you're gonna have phi n will be phi n of x will be sinus of n pi x over m. Right? That's good. So this is half of the Fourier series. I explain again. When lambda is negative, x squared is lambda, right? Because x squared is lambda, you have two roots, I square root of lambda and minus I square root of lambda. So phi x will be c1 cosine square root of lambda plus c2 sin square root of lambda. Now I'm gonna use the boundary, yes? I'm gonna use the boundary condition. Phi 0 is 0 and replace 0 here. When I replace 0 here, this is 0, this is 1, so I have c1 is 0. Now phi x will be c2 sin square root of lambda x. Now I want phi l to be 0. When phi l is 0, I plug L there, I have sinus of square root of lambda, L is 0. Sinus square root of lambda L is 0, but we know that sinus n pi is 0, which means that square root of lambda L is n pi. So lambda is negative, so you have this guy. So now I can put the n inside, right? Here I have an put n, but because when I solve it, I see that there are multiple values for lambda. This is why I denote each of them. I assign the index for each of them, right? So lambda n will be minus n pi over 2 square. Phi n x will be sinus n pi x over 2. Questions? It's clear? Yes?
What happens to C2?
So the c will still be here, right? But as we discussed in the previous class, you're gonna expand, right? So you're gonna expand like u in terms of all of those bases, right? So you have a1 sinus of pi n x over 2 plus a2 sin of 2 pi x over 2 plus an sine of n pi x over 2. Right? When you expand it, you can put a c here and you divide by c here, right? Basically, if you put the c into the basis, you're gonna divide the coefficient. So I can throw it away. I mean, the difference is they are equivalent. The difference is just a multiple. I mean, an increase in the amplitude of the wave. Right? Questions? It's clear. Right. So now let us. So I finished with the eigenvalue problem. I'm gonna spend a few minutes on reviewing how you obtain the characteristic equation from the second order differential equation. All right? It's good. So that you understand what is going on here. All right? All right. So review. So here I obtain the eigenvalues and the eigenfunction. After that, I'm gonna go back to solve the equation. But before doing that, let us review a little bit on solving second order differential equation with constant coefficient, right? So consider the equation. So you have ax second plus bx prime plus cx is 0. All right. So a, b, c are constant. A, b, c are constant. Right? It's clear? So when a is 1, b is 0, c is minus lambda, we have x second minus lambda x is equal to 0. This is the problem that we are trying to solve. All right? This is a second order differential equation, homogeneous because here we have 0 with constant coefficient. In the case that a is 1, b is 0, so review. Characteristic equation. All right. This is a second order differential equation with constant coefficient. When I replace a to be 1, b to be 0, c to be minus lambda, I get x second minus lambda x is 0. And this is the equation that we are solving over there, right? Deriving the characteristic equation. The characteristic equation. So how can I derive the characteristic equation? I gave you a hint in the beginning of the class. How can I derive the characteristic equation?
R squared minus lambda.
No, this is the characteristic equation, but how can I arrive to that equation? How? Yes?
Assume a function, the function x, let's say x is equal to e to the power x.
Yes, can you say at the back of the paper, please? So we suppose that x, let not, because x is the variable here, so I don't want the x here. Let me put phi. Right, so phi. Alright, so here I have phi. Second is phi. We suppose that phi x is e to the x. So what happened with this function? Yes?
Take the second derivative.
Yes. And the first derivative, right? Can you say the back of the paper, please? Now I'm going to take the first derivative of this function. I have r e to the x. And I take the second derivative, which is r squared e to the x. I plug it back into the equation, right? So I have what? I have r squared e to the x times a plus b r e to the x plus c e to the x is equal to 0, right? That's clear. So when I take the first derivative and the second derivative, I get a squared e to the x. This is this guy, and this is this guy. All right. And the first derivative gives me this guy and this guy. All right. Now what is next? Yes, can you say at the back of the paper, please? Now I factor out. I have e to x, a r squared plus br plus c is 0. All right. So because e to x is positive, you have a r squared plus br plus c is 0. So this is the characteristic equation. All right. It's clear. So how many roots do you have for a characteristic equation? 2. But how many cases do you have? How many? 3. Right. So you consider b squared minus 4ac. This is the delta. You're going to have 3 cases, right? Delta is positive, delta is 0, and delta is negative. Now going back to this a is 1, b is 0, c is minus lambda. What is the delta in this case? Suppose that a is 1, b is 0, c is minus lambda. I want to compute the delta. 4 lambda. Yes, can you say at the back of the paper, please? So if a is 1, b is 0, c is minus lambda, the delta will be 4 lambda. And then we have 3 cases. Case lambda is positive, and this is lambda is greater than 0. Delta is 0. This is lambda is 0. Lambda is negative. This is lambda is negative, right? This is why in the previous eigenvalue problem we have to consider 3 cases, right? Because the characteristic equation has different roots with respect to the 3 cases here, right? So the lambda is b squared minus 4ac. If lambda is positive, you have a different roots. If lambda is 0, you have different roots, and if lambda is negative, you have different roots. And the lambda in the particular case of the previous eigenvalue problem is 4 lambda. This is why you have to consider 3 cases. Lambda is positive, lambda is 0, lambda is negative. All right? Questions? It's good. Now, So case number one, lambda is positive. What happens when lambda is positive?
You have two roots.
You have two roots, right? Can you say the back of this? So you have two roots. The first one is minus b plus square root of lambda over 2a. And the second one is minus b minus square root of lambda over 2a. All right? Right. So what are the two solutions of this? Right. Because these roots makes a so because there are two solutions, you have this, right? So let us consider R1. Because R1 is a root, you have AR1 square plus PR1 plus C is 0. All right? That's clear? Which means that when you multiply e to the R1 plus PR1 plus C e to R1, this is also 0, right? Now you go back. And you go back to this, which means that you have A e to R1 x second plus B e to R1 x prime plus C e to R1 x. This is also 0. All right? It's clear? R1 is a root, right? Which means that AR1 square plus BR1 plus C is 0. Now this is 0 means that A e to R1 x second plus B e to R1 x prime plus C e to R1 x is also 0, right? You go back from here to the original equation. It's clear? So which means that you have one solution, which is e to R1 x is a solution. And similarly, e to R2x is also a solution, right? So the general solution will be a combination of these two solutions. It's clear? So Px will be C1 e to R1x plus C2 e to R2x. All right? I explain again. You suppose that the solution has the form e to Rx. You plug it back to the equation, you're gonna get e to Rx AR squared plus BR plus C. This is the characteristic equation. This, in the case delta is positive, you have two roots. All right? You have two roots, and because these are the two roots, you have AR1 squared plus BR1 plus C is 0, which means that A times ER1x second plus BR1x plus C ER1x is 0. So ER1x is also is a solution, and ER2 is also a solution. You take a combination of the two, then you get the solution in the case where delta is positive. All right? Now, in the case that I have here, what is R1? Yes? No. The R1 is computed this way. And you have I is 1, B is 0, C is minus lambda. So what is R1 in this case? Yes?
It'd be the square root of delta.
Yes, can you sign the back of the paper, please? So R1 will be minus 0 plus square root of 4 lambda dividing by 2 times 1. And this is square root of lambda. So R2 will be minus 0 minus square root of lambda over 2 times 1. And this is minus square root of lambda. Right? So this is why you have a solution of the form e to C1 is to square root of lambda x plus C2 e to the power square. Right? This is case number 1. In the case where A is 1, B is 0, and C is minus lambda, all right? The R1 will be minus 0 plus square root of lambda divided by 2, and you get square root of lambda, right? And the R2 will be minus square root of lambda. So the Px will be C1 e to square root of lambda x plus C2 e to the square root of lambda x. And this is what we got in the previous case, right? And the other two cases are listed in the previous table that I wrote for you, but the idea is the same. Questions? It's clear? Yes, I'm going to that now. Okay. So any question on this review of second order differential equation? All right. So you see how to arrive to those cases, and this is why in the first case you have exponential. But if you apply the table that I gave you in the previous class, you're gonna get the second and the third case. All right. Now let us go back to the main problem. So you have what? You have u second of x is minus fx for x from 0 to L. Okay. U at 0 is 0. U at L is also 0. Right? So you know from the previous computation you have phi n second is lambda n phi n. Phi n is 0. Is L, and this eigenvalue have the following solution. This is sinus of n pi over L x, and lambda n will be minus n pi over L squared. Right? So this is the basis that we found, and this is similar to the Fourier series. All right. Right? So this is the basis. The basis will be sinus n pi over Ls, and lambda n will be minus n pi over L squared. Now, how can we solve this problem? Yes?
Use the basis to expand, use u pi of x.
Can you say how to make a paper of this? Now you want to expand, right? You have what? You have ux is a1 sinus of n pi of n over L plus a sinus of 2 pi x over L plus a n sinus of n pi over L. All right? So you expand the solution on the basis. You're going to have a1 sinus of pi x over L plus a2 sinus 2 pi x over L and sinus of n pi x over L. All right? So what is the next step? Yes?
You have to solve for the coefficients in this case. The
Yes. So how do you solve the coefficient?
So we know an equals, or Pn equals an times lambda n. And then,
Can you say how to make it perfect, please? So now you're going to take the second derivative of this guy, right? All right? So when you take the second derivative of this guy, you have a1 lambda 1 sinus of n pi of pi x over L plus a2 lambda 2 sinus of 2 pi x over L plus an lambda n sinus of n pi x over L. Right, because of here. Because here you have what? You have sinus of n pi over L x second is lambda n sinus of n pi x over L. Alright. So from the eigenvalue problem, you're gonna get this. Alright? So from the eigenvalue problem, you know that phi n second is lambda n phi n. Alright? So when you take the second derivative of this guy, you take the second derivative of all of the bases, and you get a1 lambda 1 sinus n pi pi x over L plus a2 lambda 2 sinus 2 pi x over L plus an lambda n sinus n pi x over L. Right? Now, I'm gonna expand f So you're gonna have minus fx is a1 sinus b1 sinus of n of pi x over L plus b2 sinus of 2 pi x over L plus bn sinus of n pi x over L, etc. Right? This is so you're gonna expand minus f on this basis. How can I compute the coefficient bn? Yes?
Take the integral of the product of the second derivative and the primary function divided by the integral of the primary function squared.
Yes, can you say it back up? So now I can compute this bn by multiplying this guy with f, right? So I'm gonna have what? F bn is inner product of minus f sinus of n pi x over L divided by sinus of n pi x over L sinus of n pi x over L. Alright? So in order to compute bn, I'm gonna multiply inner product minus f with sinus of n pi x over L and dividing by sinus of n pi x over L sinus n pi x over L. Why do I have this formula? Yes?
Because it's like the orthogonal vector formula.
Yes. Can you sign the micro paper, please? This can be obtained by the following observation, right? So we have minus f, you multiply everything with sinus of n pi x over L. Right? And you have what? You have b1 sinus of pi x over L sinus of n pi x over L plus b2 sinus of 2 pi x over L sinus of n pi x over L plus bn sinus of n pi x over L sinus of n pi x over L plus etc. Right? So you inner product with this sinus of n pi x over L. This is going to be 0 because this is orthogonal. This is going to be 0 because this is orthogonal. So the leftover is just this guy. Right? So the other term will be 0. So you're going to have minus f sinus of n pi x over L will be bn sinus of n pi x over L sinus of n pi x over L. Alright? And you divide and you find bn. It's clear? So then you're gonna have bn minus of f sinus of n pi x over L dividing by sinus of n pi x over L sinus of n pi x over L is bn. Alright? It's clear? You can compute bn by multiplying f with sinus n pi x over L. Right? So when you multiply it this way, because sinus n pi x over L and sinus n pi x over L, they are orthogonal, so they are 0, except this term, right? Because you multiply sinus and sinus, so it's not going to be 0. Right? So the bn will be the fraction minus f sinus n pi x over L dividing by sinus n pi x over L sinus n pi x over L. Questions? Yes?
In homework, we've got one where the second derivative is just set equal to lambda times the equation. How would we do that? How would we do this equation here with that setup?
So in the homework, you have only to solve this equation, right?
Yes.
So basically, in the homework, I asked you to solve the eigenvalue problem only.
Okay.
Right? So what you do is just the thing that we did before expansion. Right? Yes?
Wait, so you're saying that the final answer it was asking for you, the final answer you would also be the same as what you get for the eigenvalue problem.
Yeah, so the homework was for eigenvalue problem. So if you want to solve this, you're gonna go through all of the steps that we did.
Yeah, but it's basically the same thing.
It's the same, right? So in the homework we didn't solve the equation. I asked you to solve the eigenvalue problem, right? Which is the sub problem, which is this one, right? I didn't ask you to solve this equation. I asked you to solve the eigenvalue problem, right? It's clear. All right. So now you have Bn. You have Bn. So how do I find An? Yes.
An for n is supposed to be in comparing both equations.
Yes. Can you stand at the back of the paper, please? So because this guy and this guy, they're the same, right? So which means that this is equal to this because they are the same, the factor of the same function. All right. Then you're gonna have this is equal to this because they're also the factor of the same function. And then An, lambda n has to be equal to Bn because they are the factors of the same sinus, right? So because u second is minus f. Questions? Right. So. So now you have what? A1, An, lambda n is equal to Bn. So An will be Bn divided by lambda n, and this is minus 1 over n pi over L squared times that fraction minus f sinus of n pi x over L divided by sinus of n pi x over L, sinus of n pi x over L. Right? So this gives me minus of 1 over n pi over L squared integral from 0 to L of minus f sinus of n pi x over L dx divided by sinus of n pi x over L squared dx. All right. So in this coefficient, what can you compute? Yes. Yes. Can you say at the back of the paper, please? So this you cannot compute because f is not given. This is a constant, so you need to compute this this sinus square. So now I have to compute the integral from 0 to L of sinus of n pi x over square dx. All right. So how can I compute this integral? Yes.
The trig identity where it's 1 minus cosine of double the angle over 2.
Yes, can you stand at the back of the paper, please? So you're going to use this formula again, right? Sinus square is 1 minus cosinus of 2x over 2. I apply this here, I'm going to have the integral from 0 to 1 minus cosinus of 2n pi x over L over 2 dx. All right? So how can I compute this integral? Yes? Yes, can you stand at the back of the paper, please? So you're going to split the integral into 1/2 dx and minus 1/2 integral from 0 to L of cosinus of 2n pi x over L dx. So what is the value for the first one? Yes? 1/2 of? Okay, can you send back a paper, please? So this is L over 2, right? Because this is antiderivative of this is x over 2. You evaluate at 0 and L. This gives you to L over 2. This is this. Alright? The first one, the antiderivative of 1/2 is x over 2. You evaluate 0 and L. This gives you L over 2. Alright? How can I compute the second one? Yes? The factor. Can you say the magnitude of paper, please? So here I'm gonna use the antiderivative of cosinus is sinus 2n pi x over L. I divide this by 2n pi over L. I evaluate 0 and L. And this is 0. Right? So the whole thing will be L over 2. I'm gonna plug L over 2 here. Split. So the sinus square, I'm gonna use the formula. Sinus square will be 1 minus cosinus 2 times x over 2. Right? So the sinus square will be 1 minus cosinus 2n pi x over L. And I divide that by 2. I split it into 2. The first one is 1/2 the x. So 1/2 the x will give you x over 2. I evaluate 0 and L. It gives me L over 2. The second one is cosinus. The cosinus, I take the antiderivative of cosinus. I have sinus. I evaluate 0 and L. But at 0, sinus of 0 is 0. At L, sinus of n pi is 0. So this is 0. Finally, this guy is L over 2. I plug it here. So this gives me, I have minus and minus, so I'm gonna remove the minus. So I have minus 1 over n squared. Integral from 0 to L of f sinus of n pi x over L dx dividing by L over 2. Alright? And I put, so I can simplify that. I can simplify that and I get an is 1 over n pi squared times, this is 2 over L, and then I have the integral from 0 to L of fx sinus of n pi x over L dx, right? Yes?
Isn't lambda negative? Shouldn't there be a negative sign?
There's a negative and there's a negative.
Oh, there. Oh, okay.
Yes. Yes?
The
Yes, the L is up. Can you sign it back up paper, please? Right? So then the solution will be the sum when n is going from 1 to infinity of an times sinus of n pi x over L. And you can express it this way. So you have 2 over pi square L integral from 0 to L of fx sinus of pi x over 2 dx times sinus of pi x over L plus 2 over 2 pi square integral from 0 to L fx sinus of 2 n pi x over L dx sinus of 2 pi x over L. Right? So after you compute A is given by this guy, you plug it back to the solution U, and you're gonna get sum when n is going from 1 to infinity of an sinus n pi x over L. Alright? So an is given by this factor, which means that for A1 you have this times sinus of pi x over L. For A2 you have this times sinus of 2 pi x over L, etc. And you do that to infinity. Questions? It's clear? It's clear? So basically to solve a partial differential eigenvalue problem, what you do first is to solve the eigenvalue problem. Because with the eigenvalue problem, you can have the basis, right? And after that you expand on the basis. Questions? It's clear? So I summarize the method that we have done to solve this problem. So to solve u second minus f for x is from 0 to L. U at 0 is UL is equal to 0. Alright? Step number 1. We solve the eigenvalue problem. The second is equal to lambda n. X is in 0. L. Phi 0 is phi L. 0. Right? So the goal is to solve boundary value problem. So you have u second is minus f, f is given. The boundary condition is 0 and L are given, so they are both 0. What you do is you solve the eigenvalue problem. Why do you solve the eigenvalue problem? So the eigenvalue problem will give you the eigenvalue problem give a series of solutions. Lambda n and phi n, right? So this eigenvalue problem will give you a series of solutions. Lambda n is the eigenvalue and phi n is the eigenfunctions, right? And this phi n is an orthogonal basis for the solution U. Right? So this is a theorem. This is a theorem. This is a theorem that we do not give the proof. All right? So I don't prove that. I just try to do the computation so that you have a sense of what is going on. But there is a very deep theorem inside, which says that, okay, if you want to solve this problem, you consider the eigenvalue problem. The eigenvalue problem will produce a series of solutions, phi1, phi2, phi n. This phi1, phi2, phi n will be the orthogonal basis for the solution U. So given a different f, you can still expand on this basis. And this is a very deep theorem that we don't prove. Basically, it's a Lax-Milgram theorem. This is Lax-Milgram. But we don't prove it because we're gonna need a lot of functional analysis. Step number 2. Step number 2. Since phi n is an orthogonal basis, so we can expand. Ux is a0 phi1 x plus a1 phi1 plus a2 phi2x plus an phi nx. All right, and minus fx by b1 phi1x plus b2 phi2x plus bn phi nx. All right. So right, and an will be bn over lambda n. Right? I explain again. So the reason that we have to solve eigenvalue problems is because when you solve the eigenvalue problem, you're gonna get an orthogonal basis for the boundary value problem, right? And this is a big theorem in functional analysis, and we don't go over the proof. We accept it only. So now, because according to the theorem, Vn is the basis, you can expand U in terms of Phi1, Phi2, Pn. So U is going to be A1, Phi1 plus A2, Phi2 plus An, Pn. And minus F is going to be B1, Phi1 plus B2, Phi2 plus Pn, Pn. All right? And An can be computed by dividing by Vn over lambda n. Questions? It's clear? All right, so let us go over another example. Another example is your x-axis is minus 1, your second is minus 1, y-axis is going from 0 to 1. And you have ux at 0, it's going to be 0. Ux as 1 is going to be 0. Alright? Alright. So what is the eigenvalue? Step number 1, eigenvalue problem. So what is the associated eigenvalue problem for this equation? Yes?
So we already know Phi double prime equals lambda Phi, or can we use the index still?
It's up to you.
Okay, so then like lambda double prime n equals, or Phi double prime n equals lambda n Phi. And then Phi n prime of 0 equals 0, and then Phi n prime of 1 equals.
Yes, can you sign the back the paper, please? So the eigenvalue problem will be Phi n prime of x is lambda n Pn x. For x is from 0 to 1. Phi prime at 0 is going to be 0 of Pn at 1 is 0. Right. You can remove the n. Because when we solve it, we will see the n. Right. It's clear? Questions? So to see this connection with the eigenvalue problem, there is something similar in linear algebra that that is discussed in that is also discussed in section 2.3.4 of the notes. So in linear algebra, we also have something similar. So how can we connect the two? Right? So in linear algebra, you also have the eigenvalue problem, right? So given a matrix A, connection to linear algebra, So given a matrix A, which is m times m, and a matrix F, which is m times 1, right? So you find the matrix X, which is m times 1. And so you have A times X is equal to m. For instance, you have 1, 2, 3, 4, 5, 6. 7, 8, 9 times x1, x2, x3 is equal to 5, 6, 7. This is A, this is X, and this is F, right? So in linear algebra, if I give you the matrix A, which is a square matrix, m times m, I give you a matrix F, which is m times 1, and I ask you to find a matrix M, which is m times 1. So for instance, in the case that m is equal to 3, you have to solve this matrix equation. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is A. You have to find x such that A times x is equal to 5, 6, 7. How do you solve it? Yes?
X would be the inverse of A times.
Yes. Suppose that I don't use the inverse matrix method. I want to use the eigenvalue method in linear algebra. Yes?
You take the determinant of A minus lambda I, and then you have to find the relative eigenvalues and plug it in from here.
Yes. Can you send the back the paper, please? So we will solve the eigenvalue problem. All right. So you have A times V1 is lambda 1, V1. A times V2 is lambda 2, V2. A times V3 is lambda 3, V3. All right? It's clear? So basically you have to find 4, 5, 6, 7, 8, 9. Then you have to solve for V1, V2, say this is V1, the first component, and V1, the second component, and so how do I say? V1, the third component is lambda 1, V1, 1, V1, 2, V1, 3. Right? So in linear algebra, you have to solve the eigenvalue problem. A times V1 is lambda 1 V1, A times V2 is lambda 2 V2, A times V3 is lambda 3 V3, right? Then you find the three vector V1, V2, V3. And this is V1. And this is V1. After you find the three vector V1, V2, V3, what happened? So what happened with V1, V2, V3? Sorry? Right. So in linear algebra, I want to solve for x, which is this one, right? Instead of solving x, I'm gonna solve the eigenvalue problem. I'm gonna find three vectors V1, V2, V3, such that AV1 is lambda 1 V1, AV2 is lambda 2 V2, AV3 is lambda 3 V3, right? So what happened with those vectors? Yes?
You can make a linear combination.
Yes. So these three vectors will become a basis to solve this problem. I'm gonna discuss about this later. This is 2.3.4. So see you on Thursday. All right.